Alright, I was assigned problem 5a for this assignment, and this problem asks us, it gives us a graph that looks like this, and it asks us to find the dot product of, or the integral of the dot product of the vector field and t hat. So it gives us the vector field as f equals y plus y squared k hat. And the first thing we're going to want to do is transform this equation to look like this one for the vector integral. And basically how I did this problem was split this up into 3 individual integrals and do each of them separately. So this is going to be 1, this is going to be 1, and this is going to be 1. To start with, we can look at the xy plane. So if we just look at the picture here, we can see that t hat is going to continue off in this direction. It's going to point that way. Here, I'll make it a little more visible. It's going to go like that. And then the vector field is only in the k hat direction, so it's all going to be in this direction. And these two vectors are actually going to be perpendicular, which means that we can count their dot product as 0. So for the xy plane, this vector right here is going to be 0. Next, we can look at the xz plane. So if we break this into a small little graph, it's going to look like this. We have the z and the x-axis. It goes from a down to a, or it goes from 0, 0, a to a, 0, 0. I parameterized it as x of t equals t, z of t equals a minus t, 0, and t ranges from 0 to a. So if we start to plug this into the integral here, we start with the original vector integral function. We plug in y plus y squared k in the k hat direction for f, and then we plug in -1 for dz dt. The reason dx dt isn't involved is because there's no x hat up here, so it's just times 0. And we'll finish with the integral from 0 to a of -y minus y squared dt. Now this, again, since this is in the xz plane, that's going to be this one right here. Y is going to be 0 along this whole vector. So if y is going to be constant, not only constant, but 0, constantly 0, the vector field depends on y, and it's only in the z direction. So we'd just be integrating 0, which is going to make another 0. So far, this vector and this vector are both 0. Lastly, we can look at the yz plane. We're going to do it pretty much the same way as we did up here, except instead of -y minus y squared, we're going to end up with just y plus y squared times 1. Because the derivative of dz dt here is 1. And if so I parameterize this one as y of t equals a minus t and z of t equals t. And we're going to look at an integral from 0 to a of a minus t plus a minus t quantity squared. So if we multiply that out, come down here, we have at minus t squared over 2 plus a squared t minus at squared plus t cubed over 3. Now, since we're going from 0 to a, this is going to be a squared times a, and this is going to be a times a squared. So these are both going to be a cubed, which means a cubed minus a cubed is obviously 0. So we can just count those out. And then I did take a little bit of a shortcut here. This is going to be a squared, and this is going to be a squared over 2. So a squared minus a squared over 2 is going to be a squared over 2. And then if we substitute a in for t here, we're going to have a cubed over 3. So our final answer will be a squared over 2 plus a cubed over 3 plus 0 plus 0. So there's our final answer.